Okay, we're going to work on 3.3. We're going to learn how to draw some FBD diagrams. And the first one says to draw an FBD diagram of something that's in free fall. So in free fall, you have the Earth down here, and there's an object, and the Earth always is pulling down on an object with the force of gravity, or what we can call the object's weight. So I'll put force of gravity on that right there. And technically the Earth or the object is pulling back up on the Earth, but that is a force that's being exacted upon the Earth, and we're drawing an FBD of just this object. So we only need the 1/2 of the Newton's third law pair, just the forces that are working on this particular object. Now, if this is falling in space, no atmosphere whatsoever, then that would be it. And so there would be a net force here, and that would be accelerating, obviously. On Earth, technically there's air resistance. These are going to come into contact with particles. So there's a little kind of, you could draw like maybe a friction force this way, air resistance force going up this way. As long as this force is still bigger than this, there's still a net force down. So it would still be accelerating, but it wouldn't be accelerating maybe at 9.81. It'd be something a little bit less. But as this goes, faster and faster and faster, it comes into contact with more and more and more particles. So this air resistance actually starts to build up. And as long the length that it can finally get to is exactly the same length as the weight. So when the air resistance force gets to be equal to the weight of the object, when these two are balanced out, that means zero net force. And it will no longer be accelerating downwards. It'll still be going downwards, but the forces will be balanced out, and so there'll be a constant velocity. And of course, we call that a terminal velocity when something falls down through an atmosphere. Okay, next thing we're going to look at is an object sitting on the floor. So here's an object sitting on the floor. I clearly have my force of gravity, which always is working down towards the Earth. But this thing is clearly not accelerating down, so there must be a force that balances this force out. And the force that we draw is, we consider the floor pushing up on the object. Anytime any object's on a surface, we draw a force that shows the surface pushing up on the object. And the force that we label that as is F of N. N stands for the normal force, not natural force. Some people start calling it natural force or something. It's called the normal force. Normal means perpendicular. So this normal force is always going to be perpendicular with the surface that we're on. And those would be balanced because this thing's not accelerating in either direction. So they would totally be balanced out. Okay, dragged to the right with no friction. So I can just start kind of adding things on. I would still have these two things. I'd have force of gravity. I'd have a normal force that would be equal to that. But then I'd have a force going this way, dragged to the right. And there's no friction, so there's no force going back the other way. This would obviously have a net force in this direction, and it would be accelerating. And of course, if I wanted to figure out what's its acceleration rate, I'd have this force would be, I would take this force here, because F equals ma. I would take this force, I'd divide it by the mass of the object, and I'd have my acceleration rate going that way. So that's dragged to the right with no friction. If we have dragged to the right with a constant velocity, because there is friction, the way you draw friction always goes against our motion. So whichever way we're going, you should always draw friction the other way. This would be F of F, friction. And I'm going to draw it just as long as this force is, because this thing's going along at a nice constant velocity. Sometimes students get a little confused. They think, well, if these are all balanced out, it can't be moving. No, if these are all balanced out, you have constant velocity. And it's possible that a constant velocity is 0 meters per second. So it's either not moving or it's moving at a nice constant rate. It kind of depends on what happened before we drew this FBD. Clearly, it might have accelerated up and then now it's a constant velocity, but it's still going in that direction. Okay, the next thing is drag to the right with acceleration. So all that means is, and there's still friction. So all that means is that we need to draw this force here bigger than this one, or we make this one smaller than this one, because it's accelerating to the right. That means there needs to be a net force. F net equals ma, Newton's second law. And if I want to figure out the acceleration rate, I need to take the net force divided by the mass of this object. The way I'd figure out the net force is I'd take this force, I'd subtract out this one. So it'd be F minus the friction force. That would equal ma. So if you found this force, you could subtract out that force, and you still have your leftover net force, and that would equal ma. Okay, the last one, drag the right with constant velocity with a rope at an angle. Okay, so this is where it gets a little trickier. We're going to have an object, maybe it's a box or something, and someone's like pulling on it with a force like this. Like maybe they're walking along here and they're pulling, but it's at an angle, some angle theta. That's the force. So there's the FBD. But what we want to do is we want to always make sure that all of our forces are like perpendicular or parallel to the surface. That's because it makes it easier to add up all the different forces if they're all, you know, perpendicular or they're parallel. So this force here is at an angle, and what we don't really want to use that force. We want to resolve that force into two forces, one of which is parallel and one of which is perpendicular. So this force can be drawn as actually a force coming over, and it can be drawn as a force going up. So I don't even want this force here. I just want these two forces, because then I can add 1, 2, 3, 4, and 5 forces. I can kind of just balance out the ups and downs and the lefts and rights. So this over here would be the hypotenuse times the sine of theta. So this would be F sine of the angle, and this one here would be the F cosine of the angle. And then we don't really need to worry about this force anymore. We have these two. So in this example, this is an important example because your ups and your downs have to balance each other out, because this object is never going to accelerate up or down. So that means I have an up force here. I also have an up force here. That means that the normal force and the F sine theta, those two up forces would have to equal the down forces, and we only have one of those, so it'd be the weight. And so in this case, in a lot of cases, Fn does equal the weight. So people get used to saying that's equal to that always. Well, not in this problem. This plus this would equal that. So the normal force, if I wanted to calculate that, it would actually equal the weight minus F sine of theta. I'd have to take that minus that force to figure out what that normal force left over is. And then, of course, we're going at a constant velocity, so that means this force here and this friction force should be the same length, because they're going to be equal. Okay, we're going to set those equal. That's constant force. So the force that's pulling this thing this way is not this. It's not this. It's actually this component of that. And then this force, this part of this force is actually kind of like lifting it up, trying to lift it up off the ground. Okay, which actually makes Fn smaller than it normally would have been. Okay, so those are the 6 FBDs. Hopefully that makes sense, and we're going to start kind of doing some problems here.